So continuing our discussion from yesterday. So we have understood that how a simple processor can be designed using a single bus organization. So we have understood certain terms called as data path. Data path is a collection of registers, ALU, and the interconnected bus. All together we call as a data path for execution. So we have seen that in a single bus CPU, we have identified few components which are essential for any CPU. So we identified the registers are there, then program counter is there. So after the program counter, we have an instruction register. Then we have an ALU. For the ALU to supply the two operands, so we require one temporary register called Y. And then we have one temporary register for storing the output of an ALU called Z. Then address decoding circuit is there. So these are all the different components which are essential for designing any CPU. We have also seen that how these are all interconnected using a bus. We have studied yesterday that any one data transfer can be possible on the bus because there is only one bus is there. If I am doing transfer from one register to another register, at the same time, I cannot transfer the data in one register to the outside world, that is to the memory using MDR. So any one transfer is possible. That is a limitation of a single bus organization. So we will see later how this can be overcome using a multi-bus organization. So continuing from yesterday. So we have discussed in the last class how we can able to transfer the data between two registers. What are the sequence of instructions we're supposed to give it from the control unit so that efficient transfer can happen between one register to another register. After that, we have understood how a complete arithmetic operation like addition can be performed, which involves the two operands in the registers and storing the answer back into the one of the register. So that's required 3 clock cycles or 3 steps was required for that. So today we will start with the memory read operations. So totally, I said any instruction you take it, there are fundamental few operations are there. If you understand those operations, how they're executed, using the control sequences, we can able to write the control sequences for the complete instruction. So today we will understand how the memory read operation can be executed with a CPU, whatever we are having. That is a single bus CPU. Memory read is also sometimes we can call as IO read, in the sense for IO read also the same logic is applicable. So when the same logic is applicable, whenever the input devices are interfaced using memory mapped IO. Memory mapped IO. So the moment I say memory read, I'm just here assuming that I am doing a reading on the memory for fetching an operand, not the instruction. So first we will consider we are fetching an operand from the memory, which is used for processing inside the CPU. So later we will see, after learning this one, how an instruction can be fetched. It's an extension of the same operation. Now, what are all the different blocks are involved when we want to read from the memory? So we know that memory means, so there is an external bus is required. So, and there is already inside the CPU, we have an internal bus is already available. Internal bus is there. So this is internal bus. So this is an external bus is there. Now, so whenever memory is required, we require the following registers are required on the CPU. One is MDR, other is MER register are required. So MER is connected through a switch to this one, and internal bus it's connected to another switch to internal bus. Now similarly, MDR is also connected to the external bus for writing and reading. So there is a one switch is available for writing or reading. There's one more switch is available for external bus. That is one for writing the data to the memory, one for reading the data from the memory. Similarly, there are 2 switches are available which is connected to the internal bus. Now, so now we will start using this structure and write other registers as and when required. Now let's take an example to understand memory read with one instruction. Let's say I want to execute this instruction. I want to execute this instruction. Now, whenever I want to execute this instruction, what are the steps required? It is basically adding two operands. The first operand R1 indicate that it is indirectly it's available operand, in the sense R1 do not contains an operand. R1 contains an address of the memory location. So that means that R1 will give an address. I will go to that address in a memory location. From there, I will fetch one data and bring into the CPU, then add to the contents of R2, and then the answer is stored in the R2. That means that R1 is involved in this operation. So I will write a register called R1. Similarly, R2 is involved, so I'll write the register called R2. Anything is connected through a switch, so that when required, it will be connecting. Otherwise, it will not be connected. So one for input, other for output. So I just connected. So two. Similarly, R2 also. So I connected one switch for writing, one more for reading. So now all the devices which are required for this operation are shown in the PC, in the CPU. That CPU, whatever we have designed it. So what all the involved here? MER is involved, MDR is involved, R1 is involved, R2 is involved, and external bus is there, which is connected to the memory. So I have a memory chip is there, which is connected to the bus available here. Now, so let's understand what are the steps required. Now in this one, I am now considering only one operation. What is an operation? Fetching operand from memory. Fetching operand from memory. So I'm just considering only this operation now. So what is that I'm going to write now? I'm going to write the steps. What are the steps required to fetch one operand from the memory? So my basic operation is what? Memory read. To explain the memory read, I have taken this instruction. In this instruction, one of the job is what? Fetching the operand from memory using an address which is specified in the R1. So now, so the same thing is applicable for any instruction. Whenever you want to fetch something from memory, so the same steps are required always. Now let's understand one by one what is required. Now instruction, assume that instruction is already available in the processor, in the instruction register. Now instruction register gives the instruction that you have to fetch an operand. Now I am fetching an operand, which is nothing but memory read operation. I'm doing it. So what is the first step required? I have to put the address which is there in the R1 register into the MER register, so that MER register can place the data on the address bus, external address bus, so that it will reach to the memory. Now in this case, MER is connected to the memory, and which is controlled by one control signal. It is called as MER out external. But since there is only one processor is available, in the whole system, we will always make it connected. So I assume that. So what is an assumption I'm making? That MER output is always connected to the address bus, because there is no other processor is there which can generate an address. So now I am not interested in this control, because it's always connected. Now only thing what I have to do it, what is there the data in the R1 register, that is address, should be transferred to the MER. So now I have to transfer to the MER. This is what I'm supposed to do it. Now what is the first thing I have to do it? I have to give an instruction to the R1. So R1 has got two switches are connected. So one is called as R1. Whenever I want to send data from the R1 out switch is used. Whenever I want to put data into the R1 input switch is used. Now R1 out is used because I am taking the contents of R1, putting it to MER. So R1 out. So this is the instruction, micro instruction, or the control signal given by the decoding circuit, so that R1 contents will be placed on the bus. At the same time, you have to tell which register should be opened for carrying the data what is there in the bus into that. That is MER. So I just write MER in. So now, so these two instructions will just transfer in the given clock cycle, one clock cycle, R1 contents into MER. Since MER output is already open, permanently connected, it comes to the address bus. So the memory will receive the address. Now, so now the challenge is the memory works at its own speed. The speed of the processor is different. The speed of the memory is different. If it's a cache memory, within a clock cycle, you can able to write into the memory also, or you can read within a single clock cycle from memory to the processor also, but it's not a cache memory. Let's assume that it's not a cache memory, it's normal main memory. Because many times when you have a cache also, cache miss will happen. Cache miss in the sense, the data is not there in the cache memory. So then what I should do it? I should go to the main memory and then read it. So that's why we'll assume that it's a main memory is available. It takes more time than the processor. It may require 2 to 3 clock cycles for responding to the address and giving the data. So that what is I supposed to do it? Now, since this works at a different speed, the processor works at a different speed, there should be synchronization between these two. So what is the synchronization? Now, I will initiate the read operation on the memory. At the same time, I'll wait for the data to come from the memory. So how do we wait? How do we wait? So that is why. So the processors, the decoding circuit, whatever available inside the processor. So it will generate what is called as one signal called as memory read signal, So to generate the memory read signal, the processor should issue what is called as read command to the bus interface circuit. That means that, so the decoding circuit, output of that is connected to the bus interface circuit. The bus interface circuit is the one which generates a memory read. So now I am giving one signal called as a read signal to the memory. So whenever the read signal is generated by the decoding circuit, the bus interface circuit will generate MR. So now I am informing the memory. Now I wanted to read from the memory. Which address? The address which is already placed in the address bus. So read initiates. That means that address is there in the bus. Now you provide me the data. But the data will not be provided to the memory immediately. I have to wait for that. How much I have to wait? How do we wait it? That is why most of the processors will have a signal. Is available to the bus interface circuit. The signal is called as wait for memory function complete, WMFC we call it. So for example, Intel process, this pin is called as ready pin. So that means that Intel provides a pin called ready. So the devices, external devices like memory and the slow devices will send on the ready pin 1 or 0. Whenever I receive 1 on the ready pin or WMFC, that means that the memory has finished the operation. It has read the data and placed the data on the data bus. Now we can continue. So in general, most of the process will support what is called as waiting for the data coming from the memory or the input output devices. In this case, it is called memory function complete. So what is the decoding circuit? Decoding circuit will generate a signal. The name of the signal is called wait for memory function complete. The signal name we call it as MFC. The signal name is called as MFC. The command given by the decoder to wait for the signal is called as wait for MFC. So now MFC is a signal which is generated by the memory, and this signal will be received by the processor. So some process, this signal name is also called as ready. Now what should I do it? I will be waiting for memory function complete. So in the first clock cycle, we have generated address and placed an address in the address bus. At the same time, we initiated, I wanted to read. But since reading takes some more time, I cannot continue to the third clock cycle immediately, or I cannot complete the second clock cycle immediately. Because why? I do not know how many clock cycles are required for the memory to put the data on the bus. So then I should wait. How do I wait? I have to wait. I have to keep checking at one of the pins which is being connected to the memory. So that name of the pin is called as memory function complete. So the signal what is we are giving, the decoding circuit will generate, so is called as WMFC. So WMFC means wait for memory function complete. The moment the decoding circuit generates this signal, that is a micro instruction or a control sequence, then it will keep looking at signal called MFC. So I'll be waiting till that signal comes from memory. Now, at the same time, whenever the data comes, the data should be goes through the MDR register. Since anyway, the moment MFC comes, signal is asserted, MDR should be open for writing. So parallelly, what we can do is we can enable the MDR so that as soon as the data comes, it can be written into that one. So that MDR in external, I'll enable it. So then what will happen? The one data, as soon as the data comes, then what will happen? So the data will be written into the MDR. So this is done in the second clock cycle. Only thing is, you cannot say that this completes in one clock cycle. It will take multiple clock cycles. So till the previous two discussions, whatever we have written in the yesterday's class, we are always very clear. Register to register, 1 clock cycle. So executing one addition instruction, 3 clock cycles. But only in memory read, we cannot say that it's only 3 clock cycles. It depends upon the how much of time the memory takes. So multiple clock cycles are required here. Now, assume that now after some times, after 2 clock cycles, WMFC signal is asserted, in the sense memory function complete signal is asserted. So then immediately go to the next step. So what is the next step? So already the data is there in the MDR. So now whatever there in the MDR, I supposed to write into, so register called as R2. So I supposed to write into R2 register. So then what we'll do is MDR out and then R2 in, I'll just say that. So that means that now the memory read is completed. So what we'll do is we will write a small timing diagram for this one. So which gives some more clarity how the timing diagrams can be written for a read and write operations. Now, so I will write the timing diagram with the clock cycles to start with. Now let's say all the clock cycles will be edge triggered, the positive edge triggered. Now 1 clock cycle for placing the address. Let's assume that I require around 3 clock cycles for reading from my memory. 1 clock cycle I require for writing into the destination register. So I will separate them. So 2 and then the 3 I will write like this. Now the first one is called as the step 1. That means that to do the step 1. So the next 1, 2 and 3. So this is required for the step 2. And the next 1 clock cycle, I'll assume that it is a step 3. So each of these steps, whatever I indicated 1, 2, 3. So now I'm just explaining them with reference to the time. With reference to time, all signals, how does it changes? Now, so this is a clock cycle, which is nothing but CPU processor clock. Now, so what is the first operation? If you look at the first operation, step 1, MAR is a pin. MAR in is a pin. So it will generate the control signal is generated. That means that whenever any of these signals which are indicated in any of the step, that means that these signals are valid for 1 clock cycle. Always it's valid for 1 clock cycle. Now I am generating MAR signal, so that what will happen? So address which is available on the register will be placed on the address bus. Now, so where is the address? Where is the address available? In the R1 register. So now what I will do is the address, as soon as you generate, the new address will sit on the address bus. So now this is the address bus. Now this address bus now contains the new data. What will be there in this address bus? In this lines, it is nothing but the contents of R1. So contents of R1 now is placed in the address bus. Now, as soon as address is placed, now the read signal is generated. So read signal is generated immediately in the first clock cycle itself, and it will be asserted in the bus. So now, after the read signal is generated, the read in turns generates with the help of a bus circuit a memory read signal, MR signal. So MR, this is the read signal. So MR signal is nothing but the output signal which is connected to the memory. So MR is what? A signal or a pin which is connected to the processor and to the memory, which is generated by the bus interface circuit present in the processor, which is connected to the decoder. Decoder initiate the bus interface circuit by giving a read signal. So now MR will be generated and it will be exist there MR till the completes, till the reading completes. Now, so after the read and MR is generated, now we are waiting for what is called as memory function complete. So I will write MFC. So MFC, assume that after the read is given, it takes around 2 to 3 clock cycle for the memory to put the data. So memory function complete will generate a signal, and at the end of the 3rd clock cycle, and it will be activated. The moment memory function signal is generated, it becomes high. Then immediately what will happen? So that means that the reading can start. So how does the reading can start? On the data bus. Now what I'll do is I will write the data bus. So data bus will be activated and it has got the data. So what is the data? Data is nothing but the contents of the memory location whose address is placed. It is nothing but what? It is R1 double brackets. R1 contains address and the contents of that is placed on the data bus. So when does the data comes? As soon as memory function signal is generated, the data will be placed on the bus. Now, the data will be available for one clock cycle. Within the clock cycle, it is being loaded into the MDR register. Now, as soon as this comes, the memory register also, MR signal also goes slow. So it becomes slow. So now, as soon as this MFC comes, it terminates the MR signal also, and it also terminates the data. That means the data is ready. Now 3 clock cycles are completed. The data, what is available in the data bus, is written into the MDR. Now, in the last, after written that MDR out, so one signal we are generating in the last clock cycle. That is the third step, and now it is written into the MDR. So this is how it happens here. See, if you just look at this third step, that has happened in the third clock cycle. So now totally, how many clock cycle required? So for the first clock cycle is required for putting the address and initiating the read signal. Next 3 clock cycles are required for waiting for the data to come from the memory and return into the data bus. And the last clock cycle is required to read from the MDR and placing the data into the R2 register. Like this, every step is nothing but it takes some clock cycles. Minimum is 1 clock cycle it takes. This is how the read operations happens. Now we have understood now how memory read happens. Now we will go to the little variation from the memory read. So that is called as opcode fetch. Now memory read we understood. So the same way we can also write another type of memory read operation, which is nothing but opcode fetch. So what is an opcode fetch? Opcode fetch is nothing but, it's also you can call as instruction fetch. Instruction fetch. So it is nothing but memory read only. We are reading from memory read. Memory read, but read of what? Memory read of instruction. Memory read of instruction. Now same diagram, whatever we have used in the previous case, same thing holds good here. Only thing is we are reading an instruction from the memory. What is the difference between the reading an instruction from memory and reading an operand from a memory? Number one, we'll write like a steps. In case of memory read of an instruction, we are very clear who generates an address. So who generates an address? Address is always generated by the program counter. It is not any other register. So that is why. So first step is what? We will put PC out. So as soon as when I say PC out, the contents of the program counter will be written into the memory address register. So that I should open the MER for copying the PC contents into the MER int. So now, so since here also I have to initiate a read operation, I'll initiate a read operation in the memory. But along with this, we have to do one more extra job, which we have not done in the case of the normal memory read. So let us understand that with the help of small diagram here. I said there is what is called as ALU is present inside the CPU. So which has got 2 operands, that is one operand A, other operand B. This ALU is also connected, so connected to a multiplexer as we have discussed yesterday. So multiplexer is controlled by a select line. One of the input for a multiplexer is constant 4. Another input is given from a temporary register called Y. Output of that is connected to the multiplexer, and then this is connected to here. So this Y is connected to the bus. This is Y is connected to the bus, and the B is also connected to the internal bus. Along with that, we have a program counter. So program counter. So there is one switch for writing into the program counter. There's a one switch for writing whatever there in the program counter output. Taking that one switch is available. Similarly, for the Y also, writing into the Y, there is one switch is available. So now let's understand now how this is useful. This diagram, why I have written this one. Now, so these operations are expected. We have understood in the memory read also it is taken place. Only thing is I have used a program counter instead of other register. But now, whenever instruction is fetched, it is the responsibility of the program, that is a CPU, whatever we are designing, to get ready the program counter to point to the next instruction to be executed. Always we know that what is the job of a program counter? We say generally we use the word program counter always points to the next instruction to be executed. That means that when you use the program counter contents to fetch one instruction, At the same time, during fetching, you have to make it ready, program counter, to be incremented by 4, assuming that a word consists of 4 bytes and a byte addressable memory. Program counter should be incremented by how much? By 4, so that it's ready to point to the next instruction. When should happen this one? Along with this, it can happen. So we don't have a separate incremental for the program counter. So how do we perform the addition of 4 to the PC? It is done by the ALU itself. Now, so what I will do is, as soon as the PC contents is taken and put into the instruction, put this into the MER, the parallelly what we can do is, we can make the PC contents also comes into what is called as into the PC contents. Already we can able to put them into the proper place so that I can add 4 for that. So what are the things I have to do it now? So I have to give select 4. That means that the select is there, the signal I'll be activating it, so that constant 4 I'm just pushing towards the PC because I have to perform addition to the program counter. So I say select 4. Select 4 is a signal to the multiplexer. That means that select the 4 and put this 4 into here. That I brought the 4 here. Then parallelly I can give an instruction to the processor, that is I'm going to perform an addition. So I'm just giving an add instruction to the processor also now. At the same time, so I can able to put, because already the PC contents is there in the bus. The PC contents already we brought onto the bus. So this data, what is there in the PC, it is coming on the bus. It is there here, and it is also come to the ALU also. Along with this, it has also gone to where? It has gone to MER also. It has gone to the MER also. So there is nothing wrong. I am sending the data to the 2 places. One is MER in, I've done it. The PC contents, whatever there in the bus, it has gone to the MER. At the same time, the data is also available to what? As a B operand to the ALU. Because the B bus of the ALU or the B operand of the ALU is always connected to the bus. There is no switches there. So the same thing PC is available. So I am pushing the 4 into the other place, that is A operand of the ALU. Now everything is there. Now only thing is add also I have given, add command is also given now. Only thing is, we know that in the single clock cycle, the addition can be performed. So only thing is I have to enable, so to store this answer, because ALU does not have a memory, I should hold this in another temp register. So what is the temp register? We know that through a switch, it is connected to the Z. So Z is, so it's a one temp register which holds the answer. So what I'll do is I'll make a Z in now. So Z in I'm making it. So these are the steps what is required in the first clock cycle in an upward fetch, which is not required in a normal memory read. What are the extra things we have done? These are the extra things we have done. Why these are the extra things? At the same time, I am waiting. At the same time, when we are instructing the memory to give me the instruction, at the same time, since this block is completely free, I can able to perform what? Addition of the program counter with a 4 and keep that answer in the temporary register. I cannot put the answer back into the PC now itself, because why? The bus is already used to hold this data, that is the PC contents. So now in the first clock cycle, these are over. Second clock cycle, like a normal memory read, what are the things are required? I have to wait for memory function complete. Like a normal, any memory read, I require to wait for some time. So now, as soon as wait for memory function complete is done, along with that, since answer is already there, I can take the answer from the Z. So through the switch, whatever available, I can put that answer back into the PC. Because why? The PC contents are already used, placed on the address bus. So through MER, now the PC is empty. That is PC in the sense it's ready to take the next value. Anyway, my answer is there. So I'll take the data. So what should I do it? Z out, the answer which is there in the Z, I take that and put into the PC back. Now what does the PC contains? PC plus 4. PC is equal to PC plus 4. The new value is coming to this one. At the same time, so I will write one more. I'm not going to tell now what is the meaning of this. So why you may ask the question, sir, why this is required? But it's required. So I just take this as required for a branch instructions, whether we require or not. It's not always used, but we always keep it in the there. So I've just written one extra thing, which we will discuss this in the branch instruction. So I placed Y in. So these are the steps what is required in the second clock cycle of a opcode fetch or a instruction fetch. Now what is the third instruction? Now after the once you got a memory function complete signal is received from memory, it will go to the third step. So what we do in the third step, whatever the data which has been placed on the bus on the MDR register, we will take it and then we can write that into instruction register, because we are fetching an instruction. We should go to the instruction register. So if you want, like in the previous case, we can also write MDR out external also, we can write it. So I have not written that. We can also add in the previous case, we know that. So we have written MDR in external. So we can add that pin also here. So we can also indicate one more signal, that is MDR. So in external, that is also we can write it. So MDR in. So now this is the opcode fetch instruction. So any doubt is there, you can just raise your doubt. So summarizing, opcode fetch is nothing but an instruction fetch. So which requires, so minimum 3 to 5 or 3 to 6 depends on the memory clock cycles are required. In an opcode fetch, always the program counter is used to place the address on the address bus, and always once you read from the memory, always we put the answer back into the instruction register. So this is the one difference. There is no other register. It's implied. PC is implied and instruction register is implied. So now we will go to the memory read. Next operation, memory read. So memory read is done. We will do the memory write operation now. Memory write operation. Now, so we have understood how the read both for the opcode fetch and also memory read is done. Now we will understand how memory write can be possible. Now, so what are the things are required for the memory writes? So anything we want to write into the memory, so is nothing but operand. Whenever somebody wants to write into the memory, it's nothing but we are writing an answer to the memory. So we will understand with some instruction. We'll take an instruction and then we will write it. Move R2, R1 bracket. So what does this instruction will do? Move the value what is there in R2 into a memory location whose address is indicated by the R1. That means that contents of R2 is written into the memory location whose address is indicated by the R1 register. So the whole of this operation is nothing but what? Writing into the memory what is there in the R2. So we will not now consider fetching this instruction. I will consider only one portion of that. What is that portion? Memory write only I'll consider. So now what is my job? How do you write from R2 to the memory location whose address is in R1? So only that portion I'll take it. Memory write I'll take it. Now how many steps are required? So minimum 3 steps are required when the memory is involved. Now what is the first one? So what is there in the R2 register? What is there in the R1 register? I have to place in the address bus. So MAR in, we are writing into the memory address register. From which register? From R1 out. We know that these meanings are, we know that. Now, so next you have to wait for memory function complete. But in the second clock cycle, we don't do that one, because in the second clock cycle, what is required is we are writing into the memory. But when we want to write in the memory, where is the data? Data is in a register. Which register it's there? It is there in an R2 register. So what should I do it? I will take the contents of R2. I'll put them into the bus. Which bus? Through MDR. I will put into the MDR register. MDR in, I'll do it. So as soon as I do this one, so what will happen? Whatever the data which is present in the MDR will be returned indirectly into where? Into the bus, into the data bus. So MDR in and the write, we have done it. Now, so just observe this for a moment. In the case of memory read, I do not have the data. I have to wait for the memory read should complete. Then only I can able to take the data and put into the MDR register. But when I'm doing the memory write, the data is already available with me. I can just directly write the data into the MDR register because I have already the data. So that is why we say R2 out. I'm writing into that one. So where I'm writing into which register? MDR in, I'm writing into that register. Now, so then I'll initiate the write. Now, I will assume that the data what is there in the MDR in, it's already connected to the data bus. I'm not writing that signal. Assume that it's connected already because we have only one bus is there. It's already connected to this one, right signal. So the data what is there in the MDR now is placed in the data bus. Now, the third step is I have to wait for further write. We cannot take an assumption that I have written one word, I can finish the second clock cycle or third clock cycle, I can continue. No. So when you give this command, how much of time the memory takes this and completely writes into the memory, you have to wait till that time. Only after completion of that, I should be able to go to the next step. Otherwise, what will happen if I'm writing a bulk of data or block of data into the memory? If you don't wait for this step, we will overwrite the data. That means that we lose the data. That means that memory takes its own time for receiving the data and put into the memory. So I have to wait. So in the second clock cycle, I have taken the data from the R2 register, I placed in the MDR. By second clock cycle, I cannot do it in the first clock cycle. Because the first clock cycle, the bus is used for what? So MER in and R1 out, it's used. I cannot do the second clock, I cannot do the job in the second, what is written in the second clock cycle, the first clock cycle itself. So now in the second clock cycle, it is required to take from R2. The bus is available now free. I used an R2, I placed an MDR in. So now I'm assuming that whatever the data MDR in is available, it's already automatically connected to the data bus. Now the data bus, which is connected to the memory externally, it has got the data. So now after that, in the third clock cycle, I'll be waiting for the signal. Wait memory function complete. WMSC. I will be waiting till the information comes from memory. That means that it is written successfully. So as soon along with this, I can also write MDR. So out, MDR out, enable, MDR out, enable. So that means that, so MDR in, I've written this here, the data. In the next clock cycle, MDR out, I can give it so that data will be returned onto the data bus. So why I cannot do these both? Because both are same register is involved, one after the other. I have to do it. In the second clock cycle, I return into that. I cannot do the same thing in the out enable because unless I write the data, I cannot place it. So that I've just taken it, then I return it. Only thing is we can avoid this one if permanently connect this one, but we cannot permanently connect also. So I've just given this in the next clock cycle. So wait memory function complete. So these are the three steps which are required for any memory write operation. So summarizing, memory write is always involved the 3 clock cycles, 3 plus extra clock cycle. So we have to wait for the data to come from the memory, and that will be done in the 3rd clock cycle. As soon as the data comes from the memory, it is as soon as the data, in the sense, as soon as the signal comes from the memory, it means that the data, whatever we have written in the 2nd clock cycle, has written successfully into the memory, so that I can go for the next operation, either memory read, write, or CPU operation. I can go for that. So this is the meaning of memory write. So let's go to the one complete instruction using all these operations. Now, what are the operations we have done? Register to register, we have done it. Performing an arithmetic operation, we have done it. Memory read, we have done it. Opcode fetch, we have done it. In the memory write, we have done it. Now we will take one complete instruction. So let's take, so what we can just say called write control sequence, write control sequence for execution of following instruction, add, subtraction, anything I can take it. So let's take an example. So add R3, R1. So what is the meaning of instruction? That is, R3 register will contain an address. Contents of that address is taken, plus R1 will be added, and the answer is stored back into the R1. This is the meaning of it. Now, what all the operations are required in this one? So we will list the operations and then write these steps. So now steps. What are the fundamental steps required? What were the fundamental steps or the sequence of events which was required before we start writing the control sequence? Number one, first of all, we have to fetch the instruction. Because I am writing now complete sequence. I'm writing the complete sequence. So what is the first thing I have to do? This instruction is stored in the memory. It is stored in the memory in the binary format. Assume that the whole of this instruction is one word which is stored in one address location, which is nothing but 4 bytes. I have to fetch the instruction. After I fetch the instruction, fetch instruction is nothing but what? Opcode fetch, whatever we written it. Then once the instruction comes into the processor, that is into the instruction register. Instruction register identifies what is the meaning of the instruction. As soon as it identifies the meaning of the instruction, it knows that we have to fetch one more operand. So that means that it has to do that one. So fetch the first operand. So first operand is nothing but from the memory, which is pointed by R3 register. Then as soon as we got another, that is the first operand, the second operand is already there in the processor itself. So since both the operands are available inside the processor, I can perform the addition operation, which we know that how to perform this one, perform the addition. Now, as soon as I perform the addition, I have an answer. Answer has to be stored into the R1, which is also inside the CPU. So write the result or transfer the result into R1. So these are what are the events I supposed to initiate now. So now we will write what are called the sequence control signals we have to generate for this instruction or for these events to happen. Now, so these are the steps and what are the actions to be initiated for doing these steps. That is nothing but control signals. Number one, first we know that opcode fetch. So what is required? Program counter should generate an address. It should be loaded into the MER register input, and we have to initiate a read operation. At the same time, we have to make the program counter get ready for getting incremented. So we know that. So we have to give a select 4. So instruct the adds for the addition, and also we will load the answer of the program counter, which is incremented by 4 into the Z register. Now, second, it is also similar to the opcode fetch. Already we have written it. I'm just copying it. So whatever their answer in the Z register, take it and put into the program counter. Now, program counter has got PC is equal to PC plus 4. Now, at the same time, I'll explain this later. Why in I'll write this one. So this is we'll discuss later. And then, so wait for memory function complete. Because why? You would wait for till the opcode comes back from the memory. Now, as soon as you receive the MFC signal, you get into the step number 3, and then whatever the data which has been there in MDR, so we will write into the MDR out and then IR in. So as soon as that, then what we'll do is, so now the instruction is received into the processor. Now, after this is opcode fetch. This is an opcode fetch now. Now, once the opcode is fetch is done, now you have to see that what other things can be done parallelly. The bus is free now. The bus is free. Instruction is there in the instruction register now. So who will have the instruction? It's an instruction register. As soon as instruction comes into that, in the same clock cycle, the decoding circuit knows what to be done. It knows immediately. As soon as instruction comes in instruction, it knows one more operand has to be fetched. So now I have to start what? Memory fetch. So I'm read one more operand from the memory. So what are the things for required? So who will have the address? It is nothing but R3 register. So R3 register, take it, put that into the MER register so that you are generating an address with the help of the R3 register. Then initiate a read operation. So as soon as you place the address on the address bus, give an instruction to the memory, perform start reading the operation. So the next operation is what? So next operation, we can wait for memory function complete. You are given the read instruction, you will be waiting for that. Along with that, we can make the R1, because ultimately once you get the data, I'm adding R1. Since now the bus is free, I can take the contents of an R1. I can just put into the Y register, that is temporary register. So that this is the one parallelly I'm doing. So these are the things what I can do it whenever the bus is empty. I'm just able to do R1 out. I'm taking the contents of an R1 out. I'm just putting into a temporary register Y in. So now, so R1 is out. The Y has got the data, which is nothing but the data what is available in the R1. It is being stored in the Y in. So why I'm doing this? Because anyway, the bus is empty and you are waiting for the memory function to complete. So since at the time of addition, I require the 2 operands. Now I know that operand is available in the R1 register. I can take that and put it to the Y in temporary register. So that means that one of the operand for addition is already ready, is available here. Now as soon as memory function, that means that reading is over operand, you go to the next clock cycle. So then write that data, whatever available, MDR out. And then, so when the moment you say MDR out, the data select Y means the whatever available already previously, it has been supplied to this one. since when I say MDR out, the data, other operand, what you fetch from the memory is directly in the bus. Whenever it is there in the bus, we know that it's automatically connected to the B operand of the ALU. So that means that one of the operand already there, already sitting on the operand A of the ALU. Since the moment you say MDR out, the data is coming on the bus. Since the bus is directly connected to the ALU B operand, so now you have both the data available. The only thing what you have to do, you can initiate the add operation. Initiate the add operation, and as soon as the addition is done in the same clock cycle, we know that we can able to store the answer in the temporary storage ZIN. So we have completed now. So the 4, 5, 6, we have done some overlapping. What is the overlapping we have done? We brought one of the operand whenever the bus is free into one of the temporary register. Also, as soon as the data has read, that is, we have read the data into the bus, we are performing addition also. So multiple things has been parallelly we have done here. Now in the 7th, what will happen? We have the data in the Z register. I take that data from the Z and put them into the R1 because you are supposed to store into the R1 register. So I'll just say R1 in. And whenever you write a control sequence for a complete instruction, you have to write this what is called end. So end is an indication for a decoding circuit. End is an indication for a decoding circuit when the particular instruction is completed, so that the decoding circuit knows that now it's a time for fetching the next instruction. So this is very crucial for the decoding circuit. So this is a control which knows that it's a time for fetching the next instruction. So these are the steps what is required. 7 steps are required to complete execution of one instruction. So now almost we have used all the blocks of the PC. We have used a program counter, we have used instruction register, we have used general purpose registers. So we have used MDR, we use MER. So the temporary register, everything is being used in this instruction. This is how we can able to write the control sequences for executing the complete instruction. So now we will write one instruction for branch instruction. We will write it because the branch is the most challenging to write it, but it's easy once we understand the concept. Now let's write control sequence. Write. So we will try for the branch, unconditional branch. Write control sequence. So write control sequence for unconditional, and conditional. For both we'll write in the same one, conditional and conditional branch instruction. Am I audible? Someone can answer. Am I audible?
Yes, sir. Audible.
Yes, sir.
Yeah. Okay. Now we have to understand what is a branch instruction before we continue. A branch instruction is nothing but it replaces the contents of the program counter with a branch target address. Whenever you write a branch instruction, you have a label is indicated. For example, we know that we can write a branch like this: branch, go to exit. We can also write branch, if it is greater than 0, go to the loop. This is the types of branch instruction. Two types are there. This is an unconditional branch. That means that you are guarantee that you are going to the label called exit. It's like a go-to statement. This is called as conditional branch. Conditional branch means if the condition is satisfied, then you go to the label called loop. Otherwise, you continue with the next instruction. So that means that there may be in conditional branch, there is a chance that you may branch or you may not branch also. In a unconditional, there's always guarantee that you're going to branch. So we will handle both of them. What are the types of control sequence? What will happen inside a PC? So to achieve this one. Now we will give a control signal for this one. Now the first step, we will see that what are the actions to be performed now. The first is this instruction is stored inside the memory. This instruction, branch instruction, is stored inside the memory. So I have to get that instruction into the processor. So we know that. How do we get? We know that opcode fetch. This is a standard. So from the program counter, generate an address where this instruction is stored, put into the address bus, perform a read operation. This is standard. That means that I am generating the address of the instruction where branch instruction is stored in the memory. Now, along with that, we know that we will get ready the program counter to add by 4. That means that select 4. So instruct the adder to add +4 to the program counter, store the answer in the Z temporary variable. So these are the two operations, we know that. Now whatever there in the, that is a program counter which has been, the result is there, the added value put back into the program counter. This is standard things we see in. And also we are writing one more, so which was into the y-in. I'm just explain now, it's very important where we can, it's really required, y-in, and then wait for memory function complete. Now I'll go to the third step. Now the instruction comes from the memory. After the waiting, the instruction has arrived, so I will load that into the MDR. It's automatically, it's got loaded into the MDR. So from the MDR, I will write that into the instruction register, IR in. Now till this, it's a standard. This is a standard. What are the steps required for getting it? That means that, so it is nothing but fetching an instruction. There is no differences there. Only thing is, we would like to discuss this in detail now here. Now fourth. Now as soon as the instruction has arrived in the instruction register, that is a decoding circuit which receives that instruction, understand that it is a unconditional or conditional. For the first time, for the first case, we will take it's an unconditional. Let's say it's an unconditional instruction. It's an unconditional instruction means I require to branch to a particular label. So we have discussed in the last classes, that means that whenever we branch, generally relative addressing is used. In a relative addressing, with reference to program counter, we indicate how far you have to branch. Either we have to add something to the program counter or we are reducing something to the program counter. So that means that amount of jump with reference to the program counter is indicated inside the instruction itself. That means that if I convert this instruction into a 32-bit instruction, 32-bit word instruction, so which contains what? The meaning of opcode. The opcode means what? A branch meaning is there. Then what does it contain? It contains offset. What does the offset indicate? That means that how much I have to go back from the with reference to program counter, or how much you have to go ahead with reference to program counter. That means that every branch instruction, which is a one word instruction which contains the meaning of the instruction, that is in the sense branch conditional or branch unconditional, plus it gives an offset value or displacement which gives how much or where I supposed to move, how much I have to add to the program counter so that I can move to the new location. So now instruction is already there stored here. So there is an offset. Offset is stored as a part of the instruction which is already received now. So now I am extracting only that field of the instruction register. So what is present as a part of the instruction, I am extracting that portion. So I am calling that as what? Offset field. So of IR out. So now, so instruction register contain, you have written a new instruction into the instruction register. We know that instruction contains an offset. We are taking that offset value and then it is output. It has been output from the instruction register. Instruction register gives the data. We are extracting that from the instruction register. Now, what I have to do that one? I supposed to add that to where I supposed to add this with reference to what? Program counter. Whenever we use a branch or branch condition, we are adding the offset to what? The program counter. Now, how do I add to the program counter? Whatever the value, look at this instruction now, you can understand here. As soon as the program counter will increment, we are loading the value into the y-in also. That means that why y-in is required? The incremented value of the program counter I require. When I do require, only in case of branch instruction it's required. Because always in the case of a branch instruction, we are jumping to the new location by adding to the existing value of the program counter. Program counter is always points to what? Next instruction to be executed. PC plus 4 is there in the here, is there already here. But instead of bringing again from the PC and performing an addition in the fourth clock cycle, what we can do is, anyway y is a temporary register. It is free now, as of now it's free. Along with updating the new value to the program counter, write that into the y also. So that is why y-in is always used in all the instructions, but it is not required always. When this is required, whatever the new value of the PC we return the Y in is required only in case of branch instruction, because I supposed to generate a new value into the program counter by adding an offset. So now in the 4th clock cycle, we know that already one of the offset field of the IR which is comes to the bus. Now, so which operand? It's a B operand of the ALU. Now, what is an A operand of the ALU? It is nothing but already it's available in the Y in. It's written into the Y. Only thing is I should able to instruct the multiplexer select Y. So select Y means already there in the Y, you just select the Y contents comes to the A operand of the ALU, and then addition is performed. So you have to give add because you are adding to the program counter, and the answer we know that in the same clock cycle can be written into the temporary register called Z. So now all this, what will happen? You are preparing the new value of the program counter. That value you are writing into the program counter. So whatever there in the previous addition, Z out, I am writing into the program counter the new value, and then at the end of that I say end. So that means that the whole of this instruction, what does it does? It fetch the branch unconditional branch instruction into the process instruction register, extract the offset value of that, add to the new value of the program counter, that is PC plus 4, it adds it and loads back into the program counter. So that now what will happen? Automatically you are getting ready to execute the program. Whenever the moment you say program count is loaded with the new value, it is nothing but what? It's branching to you are ready to fetch the next instruction which is at the new location. So what does at the end of this we do it? We are making the program counter have the value, new value or new address or new label address, so that the next instruction will be fetched from this location. This is how the branch instruction happens. Now what we'll do is we will make that what are the correction required for this one if it's an unconditional branch. If an unconditional branch, only the 4 is going to change. So what is the change in the 4th step? So in the 4th step, so I will write the step. As usual, offset field is taken. Offset field of IR out is taken as it is. Along with that, we are going to do what is called add select Y. Everything is required. Then Z in, we are writing it. That is all whatever there here I have written that. All this thing is required in step number 4 for a branch and condition. So I'm just writing this for what? If it is a branch which is greater than 0, this type of instruction I'm writing it. Everything is same. The 4th one I've written everything same. Only thing is I have to put one more condition here. If so in the branch and condition greater than, let's say greater than 0. So I'll be checking for a particular flag. So if instead of greater than, I'll just take equals case to make it understand. If it's a branch equals 0, I have to branch, otherwise I should not branch. So if Z is equal to 0, so I'll take a 0 flag. If Z equal to 0, then I can write, then end, I'll write it end. So what is the new things I've added here? That means that all these things will happen, but whenever branch, let's say equal to 0 means if the answer, that means in the sense whatever the condition I'm checking for, I'm checking for what condition? Let's say I'm checking for equals condition. So if it is equal to 0 means Z flag will be set. If answer is not, previous answer is not equal to 0, Z flag will not be set. That means that I should branch to the new address only when the Z flag is 1. By chance if the Z flag is 0, that means that answer is not 0, I should not branch. Then what I'll say? Then end. So immediately, otherwise it continues to the 4. So this is the only change I require. So here also the 5 steps are required, but in the 4th step, I'm just introducing one instruction small, the control sequence, which will be understood by the decoding circuit with the help of the flags, which has been inputted to the decoding circuit. We just check what happened to the 0 flag. If the 0 flag is 0, that means that answer is not 0. It terminates at the 4th step itself. So the new value of the program counter, the new value which is supposed to be loaded into the program counter will never load at the 5th step. That 5th step will never execute. So this is the how branch and conditional instructions are executed. So for both the branch and condition, branch and unconditional, that is unconditional branch instruction and conditional branch instruction, or everything is same except the step number 4, where it may terminate at the step number 4 or it may continue till the step number 5. So this is how the instructions, the sequences for different instructions can be written. So any doubt you can raise it, otherwise I'll just finish one more operation. Now, so we have understood till now how exactly these sequences for different instruction can be written. Now you have got overall idea. Any instruction if I give it, first what you have to do is you have to understand that what is the function of that instruction. You have to understand. If I give subtraction, compare, what does that instruction do? You have to understand. Because why we have to understand the instruction? Once you understand the instruction, you can get an idea that any other memory operand has to be fetched as a part of the instruction. So then any instruction execution first always required what? You have to fetch the instruction into the processor, and then only if required operands has to be fetched and you have to perform. The sequence will be similar. So now we have completely understood how to write the control sequences for execution of different instruction. What is the problem with this method? The problem in this method is the limitation is the bus. There's only one bus is there. At a time I can able to perform only one operation. If I'm transferring the data from R4 to the R2, I cannot fetch the data from the memory. I cannot read from the memory. I cannot do two operations simultaneously. So there's a lot of limitations there in the single bus organization. That is why most of the latest processors, they will go for within the CPU, within the processor, multiple buses, so that multiple operations can happen simultaneously. In the sense, I can read from the register, I can write into the register also. Both can happen simultaneously. How we can do that one? So we will now learn how we can able to design a PC with a multiple buses. So now we will just write the structure of that one. So then it's easy to write the sequence for that one. So now I will write the buses for a CPU design with 3 buses. So now what we call as, so this is called as 3 bus organization, 3 bus organization of the CPU, also called as a data path. It's a very popular method. 3 bus is very commonly used. Of course, multiple buses are there in the latest processor, but 3 buses is a good example to understand how multiple operations can happen parallelly. Now, so I will call each of the buses with the 3 different names. So 3 names. So the first bus I call this as bus A. I'll call it as. I have one more bus. I will call this bus by the name bus B. I will call this as a bus C. So 3 buses have it. Now, always we have to understand by the registers what is an advantage. So I'll just start with the register itself. Collection of all the registers we are calling by the name called register file. Whenever you use the word called register file, it's a collection of all the registers. Now, so I must be in a position to read from the registers at a time. I should be able to write into register also. Both operations I should be able to do simultaneously. So how it is possible? By introducing the 3 buses. I can write into the register I can write into any of the register from the bus C to the register. Similarly, I can read from the register at the same time when the writing is going on, because we have connected this register contains 2 buses. So the beauty is that I can read from the register R1. I can also read at the same time with the register R2. I can at the same time I can write into what? Register R4. All operations I can do simultaneously. I can read the 2 registers, take the data and give it to the ALU. At the same time, whatever the answer generated by the ALU, I can write into what? Into the register, different register I can able to do it. All in a single clock cycle. Now, so along with the register file now, I will write ALU. So which located inside the processor. Let's say ALU. So this ALU will require the 2 operands. Now, so one of the operand will be brought from this one bus. I just connect it here, 1 bus. So other operand is connected from the other bus. So this is operand A, operand B. At the same time, whatever the result comes from the ALU, I'll write into the another bus. Now you can understand that I can able to read from R1, R2. At the same time, I can able to perform addition in the same clock cycle. I can write into the different register also. All I can perform in a one clock cycle here an advantage. Now, so I have an instruction decoder. So instruction decoder will receive the data always from the instruction register. So it is written to here. Instruction register will get the data from the bus C. It gets the data from the bus. And as soon as instruction is decoder, will decode it. The portion of it, for example, offset, can be connected to the bus. So I just connected to the bus here. Now, so we know that the CPU is also connected to the memory. So the two registers are used. So let's say one register is called as a MAR register. So which generates or connected to the address bus of the memory. So MAR can be returned from this bus, the C bus. So I can write into the bus from the bus C into the MAR register. Similarly, we have another register called MDR. So which interfaces to the data bus of the memory. I can write into the MDR using the bus C. So MDR data can be read into the two buses. So at the same time, there's an advantage of connecting this to the two buses. So MDR is connected to so this bus also, MDR is connected to here also. So now we have just connected, these are the buses available. So MDR, whatever the data is available, it's connected to the memory. So it's a bidirectional, I will just connect to the memory. Now, so these all the operations, what is possible here. Now, so we will consider a program counter, a PC. So the PC will generate the new address, that is existing address will be taken, it can be added and can be returned to the program counter also. It's written like this. Instead of using the ALU for adding the 4, the most of the process nowadays, they provide what is called separate incrementer. So with the help of incrementer, you can add 4 for that. So incrementer, and I'm just connecting this to the incrementer. So we can, the PC contents will be given to the incrementer. Incrementer add the 4 and puts back to PC. So we don't require ALU to simplify the operations. So this type of putting multiple buses and connecting the different blocks is called a 3-bus organization. Now what we'll do is very quickly we will write the instruction sequence with the 3-bus organization for adding one instruction. So I will write on the right side here itself. Let's take this instruction now. And so R4, R5, and store the answer into R6. Now we know that this would have required more number of clock cycles. So now what we do is we will now write for the complete, what are the steps required for this instruction. Earlier it was required on 7 clock cycles, were 7 plus memory read, extra clock cycles were required. Now we will see that how many steps are required. Step number 1 now. So what is required in the step number 1? I'll write at the bottom. So the step number 1. So what is the step number 1 is required? First of all, I should be able to send the PC output and write into the, so R is equal to B, R is equal to B. What is the meaning of it? So the ALU, what is available here, ALU sometimes acts as a data transfer. Whenever I supposed to transfer some data, for example, R is available here now. Now the PC out, that means that PC data is available in this bus, but this data I have to take it, I have to take this data and I have to put it what? And to the MAR register. But MAR register is connected to what? The bus C is connected. Now, bus B is not connected to the bus C, but if I want to send an address on the MAR register, somehow the PC which has got the data, that is, which is generated an address, contents of it on the bus B has to be put on the bus C. Now, how do you do that one? That is why ALU is sometimes used for copy purposes. Transfer the data from one bus to another bus. ALU not only perform arithmetic operation, ALU is also designed to transfer the content from one bus to another bus. So that we will write like R is equal to B. R is equal to B means R is an output of this one. I'm just taking this value R. Now whatever there in the bus and the bus B, I'm writing this one. So this instruction instructs the ALU copy what is present on the bus B to the bus C R. So R is equal to B. B means what is available data on the bus B. This is the bus B. This is bus A. This is bus B. So now bus B, what does it contains? It contains a program control output. It comes to the B and then it has to copy to the R. So that is the meaning of this instruction. So one bus to another bus transfer is possible with the help of ALU. ALU is capable of bus transfer also along with arithmetic operations. Now I got this one. Then as usual, MER in we have to give it so that it is written into the memory address register, and it also generates this address into the memory address bus. Now parallelly, along with that, I can initiate a read signal, and also I can able to increment the PC program counter. All this possible because why? There is a separate increment is available. So the moment I say increment PC, what will happen in this clock cycle? The program counter's value is taken, returned to the MER, and is also copied this value to the incrementer to perform what is called +4. So all this can happen in a single clock cycle. Now in the second clock cycle, what should I do? I wait for the memory to complete its reading. So wait for memory function complete. In the third operation, what is required? So now let's say it enters the third line to the third step. As soon as second step is completed, that means that memory has given the instruction from the address whatever specified from the program counter. So write that instruction MDR out. So MDR out to the B bus because MDR is connected to both the buses. Now I'm writing this into B bus. MDR out B. Now R is equal to B. So R is equal to B means what is available in the B bus, I am copying to the again the C bus. So this means whatever available in the MDR register, now using this bus, it goes here and it comes to the here, this bus. Now it's ready. Now R is equal to B. Next, I will write that into IR in register because once it's available in the C bus is nothing but what? I can write into the IR register. So I will read from a different bus, got it to another bus, I am written into the instruction register IR in. Now all these operations can be possible in step number 3. Now last step, step number 4. So now what is there in the R4 out A? That means that what is the contents of the R4 register? I am sending it to the A bus. Similarly, R5, what is available? I am sending into the B bus because we know that the registers are connected to what? 2 buses. I can bring one register into one bus. I can bring another register into another bus. So that is why one operand I brought into the A bus, one operand I brought into the B bus. Now I will select that is okay, not required here. Okay. Then I give an instruction to the addition to perform an addition. As soon as addition is performed, the answer I can store into the R6. That is R6 in register because why? It is being connected to this another bus. I can write into this one and then end. So look at that. Number of operations has reduced. At the same time, temporary register Z and the Y and also one more temporary register temp will is also required in most of the single bus architectures. All the temporary registers has been removed. Now we have reduced the number of clock cycles or number of steps required to complete this instruction because the architecture has improved. What is the improvement in the architecture? 3 buses are required. Multiple operations I can able to perform simultaneously. This is an advantage of having multiple buses compared to the single bus in the PC. This is how we can design a CPU with the 3 buses. So this completes a discussion about how a CPU can be designed. So with the help of a control sequences using a single bus and also 3 buses.
Hello, excuse me, sir.